Let's look at an example now of a discrete circuit that operates as a voltage amplifier. So in this case, you might recall that this type of configuration is called an emitter follower. And so what we can see here is if we add labels corresponding to our ideal feedback, we know that our input voltage has to equal our feedback voltage plus our error voltage. So let's label, we have our base emitter voltage here, and notice I'm doing small signal labeling. So we can see in this case, our base emitter voltage is actually going to equal our error voltage. So our error voltage is equal to our base emitter voltage. And the only other voltage left if we're doing a KVL loop to relate our input, our error voltage, and our feedback voltage is this voltage across our emitter resistor, R sub E. So this must be then our feedback resistance. So again, keep in mind the basic idea with our feedback is we're taking some portion of the output and we're feeding it back to the input. If we go back to our ideal block diagrams, we saw that we multiply our output by our beta term and then add it, or rather subtract it, into our input. So what we see here though is that our feedback voltage, V sub FB, is equal to our output voltage. So because we're passing back the whole output voltage and not just some fraction, that means that in this case, our feedback transfer function, beta sub V, is actually just equal to 1. So let's take a closer look at this circuit and see if we can't figure out equations for our gain, our input resistance, and our output resistance. And so in order to do that, we're going to look at our small signal circuit. So here let's look at our small signal circuit. And so in this video, we're going to look at our closed loop gain, A sub VF. And then in the next video, we'll look at our input resistance and our output resistance, all of these closed loop with feedback. And so as you recall from our analog devices class, this is the small signal model for our bipolar junction transistor. I've labeled the three sort of key nodes here, our base, our emitter, and our collector with B, E, and C respectively. And note we don't have any output resistance, so we're ignoring the early effect and we're assuming that our output resistance is infinite. So if we want to analyze this circuit, what we can do is we notice we have two grounds here. So we can sort of flip this around so that this ground moves down to the ground on the other side of our emitter resistor. And we can also think of sort of pulling at this point here and stretching it out such that that R pi becomes horizontal. So if we do that, we'll get a circuit that looks like this. So notice we've just flipped this current source around, and so I forgot to label this, but this is our GM V pi. And notice now we have also added in our RIF and our ROF, which we'll come back to in the next video. So what we're going to focus on here is our transfer function though. So we want to see how this compares to our ideal feedback equations, and what we already know our beta sub V equals 1, but we want to see if we can find the same form for this closed loop gain as we had for our ideal topologies. So we know in general that our closed loop gain is going to be the output divided by the input. So let me go ahead and define some currents that are going to help us in analyzing this circuit. So over here on the left where we have our VI, this was our base, so we can define this current here as our base current I sub B. Notice now I've switched to using phasor notation, which is typical when we're analyzing these small signal circuits. I'm going to call this current over here, this GMV pi, our collector current. So this is IC. Notice there's no current going this way because we don't have any load connected. And then, of course, through our emitter resistor, we're going to have an emitter current I sub B. So as we expect for a BJT, and so let me change that notation, that should be a lowercase e. As we expect for our BJT, our emitter current is the sum of our base and collector currents. Okay, so with these definitions, let's see if we can't figure out a transfer function. So we notice that our output voltage is equal to our emitter current times that emitter resistor. And so sorry, let me try to be a little better with my e's here. So this is an E, our emitter current, times our emitter resistance. And as we just said, we know that our emitter current is equal to our base current plus our collector current. So we can see that from KCL at that top node there, times our RE. Okay, so now our base current, we can say is equal to V pi divided by R pi. So our base current is just V pi divided by that diffusion resistance R pi. And our collector current is GM times V pi. So now we have that. All of that is still multiplied by our emitter resistance R sub E. So what we can say then is we can factor out an R pi value as well, so that we have 1 divided by R pi plus GM times RE V pi. Okay, well, we only want to have output voltage, input voltage, and then resistor values, or this GM, which is also a sort of circuit constant. We don't want to have this V pi in there. So in order to get rid of that V pi, what we're going to do is a KVL loop over here. So we're going to do a KVL loop here, or you can think about it as being around sort of the whole outside, either way. And we're going to relate our V pi to our input and our output voltages. So coming down here to do that KVL, what we get is we have that our V pi is equal to VI minus V naught. And let me scroll up a little so we can see that in the circuit. So again, you can start any point, go any direction, and you should be able to see that V pi is equal to input minus the output. So now what we're going to want to do is we're going to want to take this expression for V pi and substitute it into here. And so doing that, we'll get that our V out is equal to 1 divided by R pi plus GM times RE times the quantity of VI minus V out. So now what we want to do is sort of split these terms. Ultimately, we're trying to solve for V out over V in. So sort of separating our two variables, we have V out times 1 plus 1 over R pi plus GM, that quantity times R sub E. So we've moved our V outs to the left side, and then on the right side we still have 1 over R pi plus GM times RE VI. So now of course we're just going to find our gain, A sub VF, by finding the ratio of our output to our input. And so if we do that using that above equation, we're going to get something that's a little bit messy. So we have in the denominator 1 plus 1 over R pi plus GM times RE. And in the numerator, we have 1 over R pi plus GM times RE. Okay, so that looks a little messy, but we can still kind of tell at first glance this has the same form as our ideal function. Oftentimes we can define a new variable here to make this a little easier, and that new variable is going to be a lowercase r sub e, so I'm going to go ahead and write it in here and then define it in a second. So this is r sub lowercase e, and then divided by 1 plus r sub capital E divided by r sub little e. So we get something that looks like this, where our r sub e, our little e, is defined as 1 divided by 1 over R pi plus GM. And so that's just the reason that seems like kind of an awkward definition, but being able to define that in terms of a resistance can make things a little bit easier to describe or talk about. And so note that this does match our ideal form, because recall we said that in this case our beta V is equal to 1. And so what that means then is that our A sub V is equal to this R sub E divided by our lowercase r sub e. So one other thing I wanted to note real quick is to take a closer look at this lowercase r sub e, so we can rearrange that form a little bit if we want. So if we sort of combine these terms in the denominator to have a common denominator, we have 1 plus R pi GM divided by R pi, at which point we can of course bring that R pi up to the numerator. So we can say R pi divided by 1 plus R pi GM, and this is then equal to R pi divided by 1 plus HFE. And so our HFE is our current gain for our transistor. So this is a useful way to get this lowercase r sub e parameter from our R pi and our HFE value. In the next video, we're going to come back and look at this circuit a little more and analyze our input and output resistance from this small signal equivalent circuit. And then in the videos following that, we're going to look at some op amp and discrete circuit examples of our current amplifier.